Hi everyone. In this small video, I'll be covering the concepts of work and energy. Work and energy are two terms that we use very commonly in our everyday lives. As well as these are two very important concepts in classical physics as well. So let's start with the definition of work and energy, and I'll be deriving a mathematical expression for both of them, and we'll see how to connect the everyday definitions with the definitions in physics. So we normally say I'm going to work. Today I feel very energetic. So when you feel very energetic, when you feel you're high on energy, you feel you can do a lot more work. So let's see how to connect the notion of everyday work and energy with the physics notion. So I'll start with the definitions of work and energy, and then we'll derive the mathematical expression for work and energy, and take it forward from there. So work is defined as the energy transferred by a force. When the force acts on an object. Now what is energy? Energy is the ability to do work. So as you can see, these both definitions are kind of circular. So to define energy, we need to know work. To define work, we need to know what is energy. So let's keep these definitions here and take forward how these definitions apply in physics. So suppose we have a body of mass m, and we are applying a force F, and when we apply the force F, the body gets displaced, say by a distance of d meters. So let us mark d on our diagram here, and the body is here. So when force is applied, the mass initially, which is at rest, it accelerates, and suppose it has moved a distance d. Then work done by the force is defined as dot product of force and the displacement. So force and the displacement, these are two vector quantities. So when you take the dot product of both of them, you get a scalar. So work is a scalar quantity. And force and displacement both are vector quantities. So now suppose we had force of 10 newtons, and let's say our displacement was 5 meters. So in that case, the work done is nothing but force times displacement, which should nothing be but be 10 newtons times 5 meters times cosine of the angle between force and displacement. So here force and displacement are in the same direction. So the angle between them would be 0. So that would be cos of 0 degrees, which would be 1. So this reduces to 50 Newton meter. Newton meter is very popularly called joule. So the work done is denoted by 50 joule. So that is the work done by the force of 10 newtons to move a mass m by a distance of 5 meters. Now suppose the force was acting at a distance, at an angle theta to the displacement. How would the expression of work be different? Let's look at that. Suppose we have a mass m here, a stationary object, and we attach a string, and let's say we are pulling it in this direction with a force F at an angle theta. Now when we pull at an angle theta, so the mass moves along the ground, and suppose it has moved a distance d in this direction. So this would be displacement because distance along this direction. Now what is the work done by this force? Work done by this force would be again dot product of force times distance, which would be here force times distance times cos of theta. So here you can see that only the component of force which is along the direction of displacement contributes to the work. So there is another component of force which is perpendicular to this direction, which would be F sine theta in this case, and there is F cos theta along this direction. So only the component of force which is along the direction of displacement contributes to the work, and F sine theta doesn't do any work from a physics point of view. So this is the work done in joules. So extending this idea, now if we have an object in circular motion, so we have a mass m which is in circular motion, and there is, when an object is in circular motion, there is the force called centripetal force here, which is nothing but mv square upon r. So r is this, and velocity is along the direction of the tangent. Now in this case, if you look carefully, the work done by the centripetal force would be 0. Now why is that? Because the centripetal force is acting inwards along the direction of the radius, but the velocity is along the tangent. At any instant the body is in circular motion. You have centripetal force along the radial direction and the velocity along the tangential direction, and because of this there is an angle 90 degree between them, and cosine of 90 would become 0. So the work done by the centripetal force becomes 0. So work is a scalar quantity, and we need to consider the angle between the force and the displacement vector to find out the value of work done, and only the component of force along the direction of the displacement contributes to any useful work. So that is the definition of work, and in our next video we'll see how to relate energy to this work, and we'll derive the expression for work energy theorem. Thank you.